All right, welcome back to our first full video, on a full hypothesis test problem. And so we'll go from the beginning all the way to the end here. So here we go. Jeffrey, as an 8-year-old, established an average time of 16.43 seconds for swimming the 25-yard freestyle. And they had enough data, they were able to calculate the standard deviation as 0.8 seconds for that sample size. His dad, Frank, thought that Jeffrey could swim the 25-yard freestyle faster using goggles. Frank bought Jeffrey a new pair of expensive goggles and timed Jeffrey for 15 25-yard freestyle swims. For the 15 swims, the average time was 16 seconds. So 16 compared to 16.43. All right, so looks like some time has been shaved off, but isn't statistically significant. You know, if it was 16.41, 16.42, 16.2, we need a confidence level. So that's what we're going to create. Frank thought the goggles that helped Jeffrey to swim, Frank thought that the goggles helped Jeffrey to swim faster than 16.43 seconds. Conduct a hypothesis test using a preset alpha at 0.05 and assume the swim times are normal, so normal distribution curve. So we go through and think about what we know here. And we know this is a normal distribution curve, looking at one group of data, and the variance is known. So this is going to be a sample z-test. And think back a few chapters ago, we calculated these air-bound means. So we use that z-score. Then we use the standard deviation over the sample size. We're going to be doing a similar thing today. So we ask, is it an average or a proportion? Mean or proportion? It's a 1 mean. Okay. State the null and alternative hypothesis. Okay, the null is, that should be a lowercase or just a subscript 0, but couldn't do it for me. So the mean is 16.43 seconds. And we want to test whether the average, or the mean, is less than 16.43 seconds with the goggles. Is this a right-tailed test, left-tailed, two-tailed? This would just be left-tailed because we just want to check the bottom end. We want to see if the swimmer saved time. What symbol represents the random variable for this test? X bar represents our random variable. To find the random variable, the average time is seconds for the 25-yard freestyle. And if the population standard deviation is known, what is it? 0.8 seconds. They give that to us in the problem. So we calculate the following. The X bar, the average from our person swimming, is 16. They give that to us. You know, if they gave you the data of all the swims, you could calculate this too. They give it to us. And we know the sample size is 15. And we're going to use a z-test because the population standard deviation was known. So here are the distributions we're using. The distribution uses our average and our average. So this is from our null, and that's 16.43. Remember, the null is the average right down the middle. Then we have our standard deviation here, 0.8, given to us in the problem. And then this is where our sample size comes in, 15. We're only using 15 swims here. You know, if we used 1,000 swims, it would be a lot different. We're only using 15, and 2 swims would be much different than 15. So there's our average, and this is calculating our sample standard deviation. So it takes the standard deviation divided by the square root of the sample size. And it's 0.8 divided by the square root of 15. I did that on my calculator, and it gives us this number here, 0.206559. Take note, the 16.43, that's our average here. So you can see this normal distribution curve. You can see how the null hypothesis, 16.43, is right down the middle. And we can see a range of times. Notice as the times get further away from the average, or the 16.43 or null, they become more rare. So we wanted to find if this person at 16 seconds if that was statistically significant. So we go to 16. So I went to below. Obviously, we have our choices above, below, between, or outside. Went to below 16. So I want to find what's the probability that we're below 16. So that tail is 0.0187. So the chance that our swimmer would be at 16 or below is 0.0187. So very small chance, about 2% chance that they would be in that region. So therefore, we take that number, we compare it to our alpha at 0.05, and it is less than our 0.05. So therefore, we are far enough into the tail region that we reject the null hypothesis. The reason is P was smaller than alpha. And here's our conclusion. These conclusions all kind of look the same too. At the 5% significance level, so that just depends on what your alpha level is, there is sufficient evidence to conclude that the true mean time in the 25-yard freestyle race is less than 16.43 seconds. So we conclude there's statistical data to support that the swimmer was faster with the goggles. And then here are the steps to do it on your graphing calculator if you want that, but it's much better on our computer.